5-mile tunnel, and one simple human error. Most water hammer happens when a turbine shuts down, but this disaster was different. By the time the crew realized the intake gate was closed, the tunnel was already half empty. They opened the gate to fix it and accidentally turned 5 miles of concrete into a weapon. This is a disaster story of Ladhon Hydropower Plant from 1950s. So this simplified layout shows the complete water conveyance system of the hydropower project. On the left side is the intake structure at the reservoir, where water enters the system through the intake gates. The reservoir operating levels are also marked here, showing the maximum and minimum water output. From the intake, water travels through a long power tunnel, approximately 28,650 feet in length. The tunnel has a very slight downward slope of minus 0.002, allowing water to flow steadily towards the powerhouse. Near the end of the tunnel, a surge tank is installed. This vertical chamber acts like a hydraulic shock absorber, protecting the system from dangerous pressure fluctuations and water hammer effects during sudden load changes or turbine shutdown. From the surge tank, water enters the steep penstock, a 611-foot pressure shaft that carries high pressure water downward to the powerhouse. Finally, at the powerhouse, the water strikes the turbine runner, converting hydraulic energy into mechanical energy and into electricity through the generators. Let's look at the layout of the intake structure. At the top is the gate control house, where operator controls the large intake gate located deep below. From this building, a tall vertical air vent and access shaft extends downward to the water tunnel, allowing both air movement and worker access for inspection and maintenance. At the bottom of the shaft is a massive rectangular gate measuring approximately 12 feet 6 inches by 9 feet 10 inches, which regulates the flow of water into the tunnel. The blue colored sections on both sides represent water inside the intake tunnel. The drawing also marks the maximum, normal and minimum water levels along with elevation references that indicate height at different points of the structure. In addition, a slot for temporary closure is provided for maintenance activities, and the shaft itself has a diameter of about 13 feet 8 inches in one section. Now, you all know run-off river hydro power plants operate on a simple principle. Water flows from the reservoir through long tunnels towards the turbine. As the water accelerates, it spins the turbine, which spins the generator producing electricity. But the water inside the tunnel is moving at enormous momentum. And this water cannot suddenly stop or disturb that flows without creating dangerous pressure forces. This phenomena is called the water hammer. You can see here in this video what is the water hammer and how surge shaft prevents water hammer. But the Ladhon accident was different. This time the problem did not come from stopping water flow by turbine. It came from air. On the morning of the incident, operators were loading the reservoir level slightly for spillway testing. A diversion tunnel gate downstream of the dam was opened to release water. Later, during lunch hours, engineers decided to reduce that discharge. Instruction was sent by telephone to partially close the diversion tunnel gate. But because the project involved Greek, Italian and American personnel, communication problem existed, and because of this communication problem, the mistake happened. Instead of adjusting the diversion tunnel gate, the assistant gate operator accidentally lowered the main intake gate feeding the powerhouse tunnel. The intake gate was almost closed. Only about 1 foot opening remained, and at that moment one turbine unit was still operating. But now the tunnel could no longer supply enough water and it started draining. At first, nobody fully understood what was happening. Inside the powerhouse, operator noticed that the turbine output was falling and the penstock pressure was slowly dropping. At the same time, the water level inside the 5-mile long tunnel kept decreasing minutes by minute as the tunnel partially emptied. As the water continued moving downhill towards the powerhouse, a massive amount of air entered the upper section of the tunnel, creating an extreme dangerous situation. The system no longer contained a solid column of water. It now contained both water and trapped compressed air. And that completely changes the behavior of the entire system. Eventually, the plant superintendent discovered what had happened. The intake gate had been mistakenly closed. Operators immediately decided to reopen it. But by that time, the 5-mile long tunnel was nearly half empty. This became the critical moment of the accident. As the intake gate reopened, water from the reservoir rushed violently back into the tunnel, while the large volume of trapped air inside became suddenly compressed. The fast moving water acted like a giant hydraulic piston, forcing pressure waves through the tunnel system because the compressed air could not escape quickly enough. Soon, the entire intake structure began shaking. Workers near the intake house heard deep rumbling sound followed by violent blast of air mixed with water. Air pressure exploded upward through an access shaft connected to the intake structure. Operators even removed a steel covered plate to relieve the pressure, but the situation only became worse. The blast became so powerful that workers started running for their lives. Moment later, windows shattered, massive doors were blown away, parts of the reinforced concrete floor collapsed, and finally the roof of the intake house was lifted and completely off the building. Eyewitnessing later reported giant water jets shooting nearly 200 feet into the air. The entire event lasted about 10 minutes, almost exactly the same time required to refill the tunnel. You might wonder why the plant surge shaft didn't prevent the disaster. So, surge shafts are mainly designed to control pressure changes when a water column is full. However, at Ladhon, the tunnel had partially emptied, allowing large pockets of air to get trapped inside. And when water rushed back in, it compressed that air violently, creating unstable air-water hammer effect that surge shaft could not absorb. Essentially, the system turned into a massive hydraulic cannon. And the aftermath was devastating. Three people lost their lives, another was seriously injured, and the plant was shut down for 2 weeks for expensive repairs. Interestingly, investigators found that while the tunnel survived the pressure, the intake structure was destroyed by the trapped air explosion. It was a catastrophic result triggered by a simple operation mistake. This disaster teaches a vital engineering lesson. Hydropower plants are dynamic systems storing enormous energy. A single incorrect valve movement or a communication error can unleash forces powerful enough to destroy infrastructure in minutes. Today, modern plants use strict operating procedures, alarm, and emergency protections to prevent this. The most terrifying part is that nothing failed structurally at first. The dam and turbines were fine. What failed was the intake control building, proving that in hydropower engineering, control is everything.